In this lesson, we will discuss the solution of minimization linear programming problems using the graphical method. So we consider this example where you want to minimize a P subject to the given constraints. As usual, the starting point would be to draw the lines which will form the boundaries of the so-called feasible solution. So the lines are simply obtained by converting the inequalities to equations. Now the feasible region is obtained from the common region that is satisfied by all the inequalities. So the starting point is to determine the regions that are satisfied by each inequality. So we start with the non-negativity conditions. Y is greater than 0. So obviously the region where y is greater than 0 is anything above the x-axis. So we use these arrows to indicate the region satisfied by this inequality. Then the next inequality is x greater than or equals to 0. X will be greater than 0 anywhere on the right of this line. So these arrows will point to the region where x is greater than 0. Now jointly, the region x greater than 0 and y is greater than 0 happens to be the entire first quadrant. So anywhere on the first quadrant, any point on this first quadrant is satisfied by these non-negativity conditions. So then the next step would be to draw the lines. So drawing lines is pretty straightforward when you consider the intercept. So the easiest way of drawing a line is to connect the x and the y intercept. For example, in this line, the line cuts the x-axis where at y is equals to 0. Then when y is equals to 0, you have x is equals to 20. Then it cuts the y-axis at x is equals to 0, and when x is equals to 0, you have y is equals to 10. So the x-intercept is 20, 0, and the y-intercept is 0, 10. So when you connect these two points, you then get the equation of this line. So this line is 2x plus 4y is equals to 40. So you do the same thing for the second line. So this is what the line looks like. Then next we want to point to the region where 2x plus 4y is now greater or equals to 40. Now the easiest way of doing that is to pick a random point above the line or below the line to see if the inequality will be satisfied at that point. So it's convenient again to choose 0, 0 as your testing point. So if you set x to be 0 and y is equals to 0, you're going to get 2 times 0 plus 4 times 0. Then you want to check if this is greater or equals to 40. Obviously 0 is not greater than 40. So which means 0, 0, the origin is not in the region that you want. So the region that you want is the region above the line. So use these arrows to point to the region above the line. So this is what your graph looks like now. Then the next step would be to include the second line representing the second inequality. So this is what the line looks like, which can easily be plotted by simply joining the x and the y intercept. Now again here you want to determine the region satisfied by the inequality 4x plus 3y is greater or equals to 60. If you pick 0, 0 as your testing point, you will find that 0 is not greater than 60, which means that 0, 0 is not in the region that you want. So the region that you want is the region above the line. So that would be the region satisfied by the inequality. So your graph then looks like that. Now, to find the feasible region, you shade the region that is satisfied by all these inequalities. So in this example, that would be the feasible region. You are just guided by the arrows. So this entire region above there is your feasible region. Then, so a feasible region takes this form. Then obviously your corner points will be this point and that point and that point, which are the points that lie at the vertices of the feasible region. So to get the equation of this line, you simply solve the two equations simultaneously. So you solve 4x plus 3y is equals to 60, and 2x plus 4y is equals to 40. You solve those equations simultaneously. So when you solve the equations, you find that the result is 12,4. So then your corner points are 0, 20, 12,4, and 20, 0. These are the points that you use in the objective function. So substituting the corner points in the objective functions, you get the results given in this table. And you will note that the minimum, because it's a minimization problem, you want to select the points that give the minimum. In this example, the minimum is 228. So then the solution of the linear programming problem is x is equals to 12, y is equals to 4, which gives a minimum of 228.